So in this video, I'm going to go over the smoke arose analysis in general because I know it's one of the trickier ones that we go over in the lab. So hopefully this will get you started as you're trying to do both the pre-lab and then when you go to do your analysis in the actual report. And I'll try to mention as I go which part is more relevant for which analysis you're trying to do, whether you're trying to answer a question in the pre-lab or if you're trying to answer or trying to prepare some of your data for your report. So the most important place to begin with is some sort of an understanding of the system that we're going to work with. So I'm going to briefly sketch here a distillation column with some reflux ratio going over here. So naturally there's a condenser that sits up here to condense all of our stuff. There are some trays in the column. We don't really care how many trays there are. And we initially start off with some liquid in the bottom. The distillate over here is accumulated in a tank, not surprisingly. This happens to be tank 5 in your experiment, but that's not really particularly relevant if you're just trying to do the analysis in general. So I'm going to get rid of that. And some of the nomenclature that we should understand is when we're talking about the bottoms tank, the reboiler tank, also called the pot tank, the total number of moles of stuff in there is going to be called W. And the concentration of whatever component we're interested in is going to be known as X sub W. So those two will always be talking about whatever's in the pot. And just for your reference, X sub W for this experiment is always going to be ethanol. Right? Whenever you see the letter X or Y, that's talking about concentration of ethanol and not the water. Right? If you need to know the water, just take 1 minus the ethanol. No problem. So how do we analyze something like this? So the first thing that we're going to do is draw our control volume, and we're going to draw the control volume around almost the entire thing with only this X sub D leaving. So this stream over here that's leaving the system is the total moles coming out is D, whereas the concentration of this is X sub D. And one thing that you should note here is this X sub D is exactly the same as Y sub D. They can be used interchangeably because the vapor that's leaving the top of the column, i.e. the distillate vapor, goes through a total condenser. So that liquid composition is the same as the vapor composition. So you can actually use XD and YD interchangeably. And you'll see this analysis does that as we go along. So like any good chemical engineer, we're going to do a material balance on the control volume that I've noted here, the red one. So if we do an overall material balance, the accumulation, just in case you forgot any of this, is equal to in minus out. Technically, there's a plus generation minus consumption, but there's no reaction going on in here, so we don't care about that. If we look at the overall balance on the entire system, all the moles that are in there, what we would end up having is the differential change in the total moles in the pot, dW, is just going to be equal to, this is as a function of time, the rate of change of dW as a function of time is just minus D. It's however many moles of stuff we're taking out. Notice that this makes the assumption, very importantly, that there is no, there's what's called negligible holdup within the column, right? There is liquid distributed throughout the column, but we're saying the vast majority of it is down there in the bottoms, in the actual tank, and we don't care about the rest of it. So again, if you think back to CENG 100, it's a 2-component system, so we can write 2 material balances. I've written the overall one. Now we can do a material balance on the ethanol. And the material balance on the ethanol, if we look at the accumulation, the most general way to write the accumulation is the rate of change in time of the amount of ethanol in there, the moles of ethanol, which is the total number of moles, times the concentration of ethanol in the bottom tank. Now, I put that in there because both of these two quantities, both the W and the X sub W, are going to be functions of time, so I can't just write W times dx dt. That wouldn't be right. So this total amount is equal to however much is coming out, which similarly to the overall balance is just minus D times whatever the concentration is of ethanol coming out, which is Y sub D. Now, you could just as easily write, instead of Y sub D, you could write X sub D there too. It wouldn't really matter one way or the other. But we're going to go with Y sub D. So now we're going to use our good friend, the chain rule, in order to expand this term so that we can get it into something that we can actually use. And we're also going to take this dt and send it over to the other side of the equation. If we do both of those, what we will find is that we have w first times the derivative of the second is w times dx sub w, plus the second x sub w times the derivative of the first, which is dw, is all equal to y sub d times a quantity minus d times dt. And if you're playing along in your book, well, actually this is not a numbered equation in your book just yet, so we can't play along. Now what we're going to do is we're going to take this overall balance and put it in down here. So you can see if we rearrange the overall balance, we can represent this term as simply d sub w, right, from our overall balance. So let's write that in there. If we do a little bit of rearranging, what you will end up finding then, and I would encourage you to do this on your own, if we put all the stuff that has to do with dw on the left-hand side, what you'll find is that we can integrate dw over w, and that integral will be equal to the integral of 1 over yd minus xw dxw. Right, and so this is what's called the Rayleigh equation in your book, and I will variously refer to this as the Rayleigh equation, or the actual interior, just the integrand of that I will sometimes call the Rayleigh integrand, but generally this is the Rayleigh integral. This now, if you're playing along in your book, this is equation 13-2, or very nearly equation 13-2. As soon as we put the limits of the integral in there, so I'm going to move this integral over a little bit so I've got some room here. Move that one, oops, and give me some space here, shift that over to the side. At this point, we need to apply the limits of integration. So we will integrate on the w side from the initial w, the initial number of moles in there, to the final number of moles, and similarly xw naught over to the final number of moles in the pot, which is xw. The term on the left, we can actually evaluate that because we know something about it. This one is not a problem. This will just become the natural log of w over w naught. The problem comes really in how in the world do we evaluate this term here, because very importantly, yd is a function of xw. So there's no good way, well, actually, that's not true. There is a good way to figure out what that integral is, but that's not actually going to come until later in this video. And so for now, all I want you to do is know that we can solve that particular integral. There is a way to do it. It doesn't require any knowledge of your experiment. We can do it entirely numerically. So all I want you to do at this point is know that that integral is known. And we're going to approximate that integral. At the end of the day, we're going to come up with a way to call 1 over yd minus xw some function of xw. We don't know what that function is yet. We will get to that later on in the video, but know that we can figure out what it is, right? That part is a subpart of solving the entire problem. So generally what we want to do, now that we have our working equations, and the two that we are most interested in is our Rayleigh equation. We need one more to round out the whole system. So if I'm going to start another slide here. If we do one more thing, if we look at just the stuff going into the pot, right? So in your experiment, this corresponds to tank 5. But if we look at just what's going into that pot, and we want to know as a function, or sorry, over a given period of time, what is the average composition in our distillate? What is the average composition of ethanol in our distillate? Well, if you remember back to definitions, if we just want to know what in the world is a mole fraction, the mole fraction of ethanol in the distillate is the number of moles of ethanol over the total number of moles in the distillate. And now we can use a little bit of logic to figure out what both of these are. The total number of moles that are in the distillate has to be however many moles came out of the pot, which is the number of moles that we started with in the pot minus the number of moles in the pot after some time t, little lowercase t. How many moles of ethanol do we have in there? Again, that has to be the difference in the number of moles of ethanol that started off in the pot, which is W naught, X naught, minus however many moles were left in the pot after some time t. So W sub t times X. I'm going to call this actually X sub WT, just so that you're reminded that that is the number of moles of ethanol in the pot after some time t. And to make that a little bit clearer, I'm also going to go back and add a subscript onto this to let you know that this was the initial number of moles in the pot of ethanol. Well, X naught, XW naught times W naught is the number of moles of ethanol that was in the pot. XW naught by itself is just the concentration. So this is the other equation that you will need. And again, if you're playing along at home, this is equation 13-6. They call it XD average, and they actually spell out the word average. I'm lazy, so I'm just going to call it XD with a bar on top. It's the same thing. The other equation that we have is the natural log of W over W naught is equal to this Rayleigh integrand, XW naught to XW. I'm now going to call this XW sub T for any time T, and I'll slap a little T on my WT over here just to make things a little bit more clear. Times this, which I'm just going to write it once here, 1 over YD minus XW. But remember, this is somewhat misleading. We're going to come back and figure out how to calculate that numerically here in a minute. So for the moment, I'm actually going to erase it and plug in this F of XW. Remember how we defined that just a minute ago? Times dXW. And the reason that I'm doing this is to point out that we will be able to evaluate this integral, right? When we go to do our analysis, we will be able to complete that integral, evaluate that integral, once we've figured out what f of x sub w is. And for that, we're going to have to switch over to a different program, but for now, we're okay. And so these are the two working equations that you're going to have to use to solve any kind of these batch distillation. So again, this is in your book, this is equation 13-2. So these are the two equations that we need. Now, how do we actually use them? Well, your book goes through in one direction. I'm going to go through, well, what the hell? Let's do them both. If you're trying to do your prelab, so let me divide these two screens, and we'll say if you're trying to do your prelab versus if you are trying to do not your prelab, but your experiment. So these will be a little bit different. Your prelab is actually harder than your experiment, but I want you to know a little bit more than the bare minimum. Your experiment goes over here. So if you're doing the prelab, what you have in the prelab is you are given a bunch of initial information. You're given W naught, X naught, and you are given, in fact, a desired XD average. And your goal is, how do I use smoke arose in order to figure out what XD average is? So once you're given those values, the first thing that you need to do, you're also given, number of stages. I guess I should add that here. You're given number of stages, a particular reflux ratio, and that kind of stuff. So the first thing that you need to do is determine what is that f of x. Once you know what the f of x is, the rest of this goes fairly smoothly. Once you know f of x, which again we'll get to how you actually evaluate f of x in a moment, once you know f of x, then you can go through the following solution procedure, which is we will guess xw at some time t. Once we have guessed xw at some time t, we can, by using equation 13-2, come on, pen. Sorry, pen's giving me some trouble. Using 13-2, the Rayleigh integral, we now know the limits of our integral. We know xw naught because that was given to us here. We also know xwt because we just guessed that. Presumably we had some way to determine what f of xw is. We'll get to that in a minute. Therefore, we can completely evaluate the right-hand side. It will just be a number. We also know w naught, and therefore we can solve for wt. So that's what we're going to use the Rayleigh equation for. So once we guess our xwt, we will use the Rayleigh equation 13-2 to find out what wt is. Once we know wt, note that that is the last thing that we needed to learn in order to solve for an xd average. So if we look up here at equation 13-6, we know w naught, it was given to us, as was xw naught. We guessed an xwt and calculated the corresponding wt, and of course we know the ones in the denominator. So from that single guess of xwt, we can now also calculate an xd average. Now the question becomes, is that xd average equal to whatever the target is? So in the pre-lab, I asked you, I think it was something like, figure out whatever it takes in order to get 70% as an xd average. So this comes over to here. If the xd average is not the one that we want, then we go back and we calculate whatever that xwt is again. We make a new guess for xwt, calculate another wt by the Rayleigh integral, and then use our just a simple mass balance, which was 13-6, to figure out what xd average is, and we just keep going until we get the average that we want. Once we have it, then we're done. That's the end of that analysis. I think I asked you how many moles have to be distilled, which is just the number of moles that came out, which again, you've already calculated along the way. That's just this value up here, which is w naught minus wt. That is the number of moles that you had to distill. So that little iteration process is that step 3 there on the pre-lab is not something you have to actually do in the experiment, but it's nice to get done. So how does the experiment compare? So in the experiment, instead, what you will have is you will have a known xw naught. You can get that through a flash calculation. You will also know the number of moles in the tank initially. So if you know the volume of stuff in the tank and the composition, you can use density and a molecular weight to get a number of moles. This is where the difference comes in. You will also know at some time t, you will know the concentration of ethanol in the pot at that time t. And so this is where we begin to deviate from the pre-lab. We're going to say if we know all of these, and of course you'll know whatever reflux you set and the n as usual. The question becomes then, how do we compare the xd average that we're going to measure? This is something else that you're going to measure, so I'll abbreviate that as xdm for the measured value. The question then becomes, how do we compare this, and does it compare favorably, to the xd average that we're going to calculate theoretically, which I'm not going to use a t because we've got enough t's, so I will abbreviate that as SR, as the xd average as predicted by Smoker-Rose. So that's the comparison that we're trying to make. Don't forget to measure all of those values. We need them all in order to make this measurement. So just for clarity, I'm kind of running out of room down here, so I'm going to move this x sub dm up here. Don't forget that we do actually know what XDM is. That's the average the average composition in your distillate, which is tank 5. So now how do we use smoke arose? Given these initial values, the very first thing you're going to do, just like your prelab, is determine f of x. We need to know what that value is. Again, we don't actually need to know any of the experimental data in order to do that, except we will need a little bit of input from R and N, as we'll see when I show you how to solve that. But once we have f of x sub w, if you think back to what we did on the prelab, the first thing we did was guess xwt. We don't have to do that anymore, right? The first thing that we can do on this analysis is, given all the stuff that we know, we can go directly to the Rayleigh equation, or the Rayleigh integral, which is 13-2. Is it 2 or 6? 2. Right, 13-2. Immediately from that, we can calculate the number of moles that should be in the tank at time t as predicted by the Rayleigh equation. So it is possible that you could measure W sub t. There are actually lots of different ways that you could compare theory to experiment. This is just one of them. So what I'm going to assume in this particular one is that we don't know what Wt is. We're going to use the Rayleigh equation to calculate the number of moles in the pot after some time t. Once we know W sub t, we can immediately write by 13-6, sorry, pen's acting up there, 13-6, we can immediately calculate xd as predicted by the smoke-arose equation, the average composition. We then compare that to something like xd average that we actually measured. And so you can do this as many times as you want, at as many increments of time as you want. So for example, a nice plot that you might try to create for your report is something like time on the x-axis and xd average on the y, and you can have, you know, a measured point here with an error bar, another measured point here. Maybe you're measuring every 10 minutes, something like that. And then you can compare the value as predicted by smoke arose, which I've said here are the blue X's. That would be a fine plot to put in your report. But at any rate, you can see here that step 3, which was somewhat more complicated for the prelab because it involved an iteration, does not require an iteration for your experimental data. Given what you're given in step 1, so you're going to measure xw naught, w naught, xwt, all of which have to do with the pot concentrations. Obviously, you'll set the reflux to something. You'll know the number of stages. The only other thing you need to measure is the average distillate composition at whatever time you choose. You'll then use the Rayleigh equation, 13-2, to calculate Wt, and then the simple mass balance of 13-6 to calculate the average distillate quantity as predicted by smoke arose here. Once you have that, you compare that value to your experimental value. So that's in essence the analysis that you're going to be doing. But as you'll notice, I kind of overlooked something that was rather critical, which is that f of xw. How do we figure that out? That's actually something that takes a little bit more effort and does require some iteration on your part. And I would recommend getting a separate piece of software to do that. Don't try to do it by hand. But just to demonstrate what that looks like, let me switch over here and I'll get a different piece of software out. So here's a little Excel demo that I made up to figure out what that f of x function is. We need to be able to pick an arbitrary set of x sub w and find out the related y sub d for each one of those so that we can figure out numerically what the relationship is between yd and xw. And then from that, we can calculate that f of x parameter that's actually in the Rayleigh integrand that we need to evaluate. So what you can see here on the left is just a simple XY diagram that is pretty common for a McCabe-Thiele analysis. And just to go over the relevant parts, I've put an equilibrium curve line on here, which is for our ethanol and water system. The blue line that's on here is this number of stages that we'll step off. So again, in this simple example, I just assumed that we have 2 stages because it's easy to show on something like this. And then the red line is the operating line. And so for this example, I've chosen a reflux of 3. So the slope of this red line is 3/4, or 0.75. I've also marked a couple of points on here of interest. The first one is this red point, which is where the operating line intercepts the 45-degree line. And I've also marked where the last stage intercepts the operating line. So if you'll recall from McCabe-Deely, those 2 points need to be right on top of each other. But the way that we're going to do this, the way that the book goes through it, we don't know exactly where those 2 points lie to begin with. So generally the procedure is as follows. The first thing that we're going to do is guess a random x sub w. I mean, obviously it has to have some amount of importance. A good one to start off with is actually the initial composition in the pot. So for example, the book gives you 0.2 as the initial composition in the pot. So you can see that xw naught is 0.2, but now all I know is the slope of this line, of the operating line, but I do know that my last stage right here has to end right on top of the 45-degree line. So I need the intersection of my operating line and the 45-degree line to be in the same place. The way that we go about fixing this is we can't change the slope because that's set by the reflux, but we can change the intercept down here of the operating line. So right now the intercept of the operating line, which I've called B in this example, is 0.1. And you can see as I increase the value of the intercept, so now it's 0.11, those 2 points are getting a little bit closer together. So if I continue to increase that, you'll see they get a little bit closer and a little bit closer until right around here, they're pretty close to right on top of each other, right around 0.6. If I go more than 0.6, then my intercept moves away in the other direction, and that's too far. So as I pull that intercept down a little bit, I get pretty close. It's somewhere between 0.6 and 0.7. I wrote a simple macro to figure that out more precisely, which basically iterates on the slope B here until those 2 points are on top of each other. So if I click this button, it'll line them up right on top of each other. The plot itself doesn't look like they're on top of each other, but numerically they are. That's just an artifact of the way that Excel plots things. And so you can see now I have the sort of ideal behavior of McCabe-Deely, which is I step off to my equilibrium, over to my operating, up to equilibrium, over to operating, and I wind up right on the 45-degree line like I'm supposed to. And so I can take that corresponding y sub w over here, which I've calculated here, that's y sub d, and I'm just going to start tabulating these data. So the xw I have is 0.2, the corresponding y sub d, which again is simply stepping off the number of stages I have to the operating line that I've determined was appropriate for that particular xw, and the corresponding y sub d is down here. It's about 0.65, which I've also listed right here to be a little bit more precise. So I'm just going to round that to 0.65. And then I calculate the value of the integrand that I'm going to need for the Rayleigh equation here. So I'm going to take 1 divided by the quantity of yd minus xw. And you can see over here on my plot of 1 over yd minus xw against xw, I've added my first point here. So this is the somewhat tedious part of the Smoker-Rose equation, which is I'm going to need about 5 or 6 of these points so that I can get a good idea of what this function is, the 1 over yd minus xw, as I vary xw. The nice thing is, once I have those data points, I probably won't need to ever calculate them again for the given reflux and the number of stages that I have. So just to show you this doesn't take horribly long, let's pick another one of 0.1. You can see that shifted my xw to the left, and now I need to adjust my b to get it where I need to. If I click my button here again, it'll match it up, and I can add that number 0.1 and 0.61. I'm just going to drag that number down. You see I get another point here. Let's add another one, let's say maybe 0.05. We'll go far to the side, match those. You can see that once you have this code set up, it really doesn't take that long to figure out most of these values. I'm going to go ahead and add about 5 of them. So it looks like I could use one around 0.15, match those 2 points. So 0.15, 0.63. And you can tell I'm rounding these numbers a little bit. You don't have to carry that enormous level of precision on there because you probably don't know it to that level of precision. And then we'll capture 0.25 just to make the plot look pretty. So 0.25. And the corresponding YD is 0.66. One thing to note, it is useful once you have completed these to simply sort them so that they go from largest to smallest. That'll help us out momentarily. Those appear not to be sorting for some reason. So I'm going to have to sort these by hand, which good luck if this actually works. Yeah, that's not going to work. Okay, there we go. Sorry, little interface problem there, but it's all sorted out now. So the reason I did that is so that now I have a few of these points that represent how this quantity 1 over yd minus xw varies as xw. To make my life a little bit easier, I'm going to do a little bit of regression on it to give me a function that'll work a little bit more smoothly. So you can see here that the line that I've added to it, let me make it a little bit brighter for you. So red, no dashes, nice and thick. The type of fit that I've done here, this is where I have to use some engineering judgment. All I need is a fit that accurately represents this data, but I would assume that it doesn't vary in any particularly crazy way, right? It should vary relatively smoothly between these 2 points. So linear usually doesn't work, logarithmic, not that great, power, not bad, or sorry, not good. If you do polynomial, usually you get pretty good representation from a polynomial. So this is just a plain old second order polynomial. It seems to fit that data fairly well. If you up the order of the polynomial, which if you display the equation on the chart, you can see what I mean by upping the order. Here it goes up to x squared, which is second order polynomial. On the other hand, if I go up to something like a third order, I do actually get a better r squared. So if I show the r squared on there, the r squared will go up. So here it is at 2 and my r squared is 0.98. Here it is at order 3 and my r squared has gone up to 0.99. But that doesn't necessarily mean it's a better fit, right? Especially if you go up to something like a fourth order. Sure, the r squared is 1. It goes right through those points. But you can see it's got some odd waviness in there. That's probably not particularly physical. So for the level of approximation that we're interested in, it's easier to just go with a second order polynomial and leave it at that. The other thing to remember is when I'm choosing these arbitrary values of xw to populate this plot, the only thing that I need to make sure of is that I capture all the xw's that I'm going to measure experimentally. None of these points were actually taken from experimental data, right? If you look over at the table that I was using over here, let me put this back. There we go. If you remember this table over here, I was just picking these XW values entirely arbitrarily, right? They had nothing to do with the experiments that we run. Nevertheless, when we go to evaluate the Rayleigh integral itself, we do need to make sure that this data series that we've selected here captures the range of interest. So it had better not be the case that any of my XW compositions get outside the range of 0.25 to 0.05. If they do get outside that range, I need to come back to this system that I've set up here, add another point, and capture that behavior. So for example, if after I come back to my experiment and I find out that, oh, my XW final ended up being not 0.05, but maybe all the way down to 0.025, I'd have to come over here and say, okay, this is not 0.25, but the lowest I had was 0.025. And now I need to adjust my slope again, like this, get that one close, and add this additional point onto my data plot. I'm not going to do that because I don't need to do that. But nevertheless, that's what you'll need to do if any of your experimental data are outside that range. Otherwise, as long as you've captured that range, you can pick whatever points you want, and as many as you want, as long as you have at least about 5, to represent this curve. So we can now flip back to our original derivation. Remember, everything that we were just doing was trying to figure out how do we come up with this magical fxw value that's sitting here. What was the procedure to do to get that? Well, that's what we were just doing, was figuring out how do we find out what f of xw is. And as I mentioned before, that's how you incorporate information about your system into this analysis. Remember, the f of xw needed information about the number of stages, the reflux ratio that you had. If you want to be, super fancy pants, you can also put in a stage efficiency in there. But at the end of the day, we have figured out now what f of xw is. And just in case that's not entirely clear, that last step that we did was essentially saying that f of xw, if you go backwards in time a little bit, it's nice because this is a video, you'll find that we found f of xw is equal to about 17.429, give me some space there, come on pen, 429 times xw squared minus 3.1129 times xw plus 2.1369. That is f of xw. So now in all of our analysis procedures, remember we still have that we need to figure out what is natural log of w over w naught, which is equal to the integral of xw naught to xwt, there's a wt back there, times this 1 over yd minus xw times dxw, which again we had approximated. We took out that integral and said, well, I don't know what that integrand is, but we'll come back to it and figure it out later. And we said, okay, that's f of x. And we tried to figure out what that was. And in order to do that, we went into Excel. And we had Excel do a little bit of heavy lifting for us. Let me pull that. Actually, I'm just going to flat out erase all of that. And what we found was we can take this exact equation from Excel. Come on, you can do it. You can do it. Copy that. Take it down here. Paste it into our expression for f of x. And integrate that entire thing from here over to here. That's a polynomial, so that should be pretty easy to integrate. dxw. Now all we need to know are the limits of integration. And again, the limits of integration are nice. They're fairly easy. If you're doing the prelab, you know one of them. You'll always know xw naught. If you're doing the prelab, you'll have to guess xwt, but in your actual experiment, you will be measuring xwt. So you'll have actual numbers for the limits of those integrals. From this, you can evaluate w sub t, and then eventually you can then go over to xt average, which again was defined as equation 13-6 in your book, or if you flip back a minute, you can read it there. And at least in your experiment, that's the one that you're going to compare to what you can measure experimentally. So I hope this was helpful to get you pointed in the right direction for solving both the prelab and your actual data analysis when you go to complete your experiment. Thanks for watching, everyone.